So this says that we have a 2-foot cube rigid tank that has saturated refrigerant. And then it gives us some information about the refrigerant. And then it says there's a valve at the top of the tank that's opened, and we allow vapor to escape, and at the same time heat's transferred to the refrigerant so that the pressure in the tank remains constant, and the valve is closed when the last drop of liquid in the tank is vaporized. And what we want to do is determine the total heat transfer for this process. So what we're doing, we're starting out with a saturated mixture of refrigerant in a tank. We're going to add heat to, and we're also going to allow refrigerant to escape until the refrigerant is all in the vapor phase. And so since we're losing some refrigerant from the tank and we're not replacing it, this is an unsteady flow problem because the mass inside the tank, the mass of the refrigerant in the tank is changing with time. So what we want to do is draw a diagram and write down the information we have. So problem setup. So we have this tank, and I'm just going to put that it's connected to this valve, and this has refrigerant, and let's see, so we know that there's going to be some heat in, and it says that it's a 2-foot cubic tank, so we have that the volume is equal to 2 feet cubed, and since it's rigid, that means that the volume doesn't change, although we do have a mixture of liquid and vapor, so there's going to be different volumes of the liquid and the vapor in the tank. And then it tells us that initially the refrigerant is at 160 psi absolute, so P1 is equal to 160 psi absolute. But then it said that like if we go to, so heat is transferred to the refrigerant such that the pressure inside the tank remains constant. So therefore we know that P2 is equal to P1. And it also gives us that this starts out as, let's see, so it starts out as a saturated mixture. And it tells us that 5% of the volume is occupied by the liquid and the rest by the vapor. So in this saturated mixture, we have that the volume of the liquid is, see, 0.5% of the volume, so 0.05 V, so this is 0.1 feet cubed, and the volume of the vapor is equal to, so there's 95% vapor because it says the, so initially 5% of the volume is occupied by liquid and the rest by vapor. So this is 0.95 V, which is 1.9 foot cube. It tells us that the valve is closed when the last drop of liquid in the tank is vaporized, so I'm going to say that the final state is saturated vapor. Alright, so this is basically the information we were given. Now let's make some assumptions. So first of all, we're going to assume, so this is unsteady flow because the mass is changing with time, but we're going to assume uniform flow. And this means that the properties of the refrigerant aren't changing as they flow out. And so basically the state of the fluid leaving is constant. And we're also going to assume that the change in kinetic energy is 0, the change in potential energy is 0, and that there's no work. So there's some heat in, but there's no indication that there's any work in this process. So we have our problem set up, our assumptions. Actually, what is it that we're looking for? Determine the total heat transfer. So we're looking for Q. So basically we need to know how much heat we need to add to keep the pressure in the tank constant while we're discharging some of the refrigerant. And so now let's write down our equations. So first of all, we want to do a mass balance. We know that the mass in minus the mass out is equal to the change in the mass, and there's no mass in, so that's 0. So the mass out is just equal to m2 minus m1, and then I'm going to multiply through the negative sign, so m1 minus m2. And now we want to do our energy balance, and I'm not going to write down the full equation that we had derived earlier. I'm just going to go to the first law for discharging. But just remember that this form of the equation has a bunch of assumptions built into it, so you need to make sure they apply to your problem. And the one assumption that we made that might not be true for all problems is assuming that the kinetic energy is 0 and assuming that well, actually we didn't assume the work was 0, so sometimes your kinetic energy might not be 0 and or your change in kinetic energy might not be 0, so you'll need to consider it. So, but we're going to use this first law for discharging because we know that the assumptions that were built into it apply for this equation. So this is Q minus W is equal to M2 U2 minus M1 U1 plus M out H out. And the work is 0, so we're just going to take that out. So now what we need to do, we need to figure out what we know and what we need to look up. So first of all, we don't know the mass of the vapor or the liquid, but we can get those because we know the volume, and we can look up the specific volumes at the particular states we're interested in. So we can get these. We can look up the internal energy at state 1 and state 2. And then for the mass out, we're going to do the same thing. We know the volume, and we're just going to look up the specific volume at the conditions for the outlet, and then we can look up the enthalpy for the outlet. So let's look up our data now. And really the hardest part with these particular problems is just keeping all of your data and terms organized, because now you're dealing with a changing state, but you're also dealing with fluid flowing in or out of your system. So just label everything and try and keep everything really clear. So let's start with the outlet. So I'm going to start with the outlet, and then I'm going to do state 1 and state 2. So first of all, we know that P out is equal to 160 psi absolute, and we have vapor escaping, so we're just going to say it's a saturated vapor. So then what we can do is we can go to the table and we can look up out. So the specific volume out is equal to the specific volume of the saturated vapor, which is 0.29339 feet cubed per pound mass. And the enthalpy out is equal to the enthalpy of the saturated vapor, which is equal to 117.2 BTU per pound mass. So we have the outlet. Now we want to do state. And so we have at state 1, we know that P1 is 160 psi absolute. We know it's a saturated mixture, so that was given. And so what we can do is, so what I'm going to do, we're going to need to calculate the masses of the vapor and the liquid, and we're going to use the specific volumes to do that. And so we need the specific volumes of the liquid and the vapor, And then we also need the internal energies of the liquid and the vapor. So I'm just going to write these down now, and then we'll work with them later. So 0.01413 feet cubed per pound mass. The specific volume of the saturated vapor is 0.29339 feet cubed per pound mass. The internal energy of the saturated liquid is 48.11 BTU per pound mass, and the internal energy of the saturated vapor is 108.51 BTU per pound mass. Now let's look up the data for state 2. So at state 2, P1 is still 160 psi absolute, but now we have a saturated vapor rather than a saturated mixture. So V2, the specific volume at state 2, is equal to the specific volume of the saturated vapor, which is 0.29339 feet cubed per pound mass. Now I already wrote this down up here, but I just want to write it again so I have all of my information with the corresponding states. So U2 is equal to the internal energy of the saturated vapor, which is 108.51 BTU per pound mass. Alright, so we have all of our data. Now let's go back to our equations, and I'm going to write down the equation for the energy balance, and then we'll look at how we're going to solve this. So we have the Q is equal to M2U2 minus M1U1 plus M out H out. So we have U2, U1, and H out. What we need are these masses. So first of all, we know that the mass, let's just start with mass 2. This is equal to the volume of the tank over the specific volume at state 2. And the reason why is because we just have a saturated vapor that's taking up the entire tank. So we know that this is 2 feet cubed over 0.29339 feet cubed per pound mass, which is equal to 6.82 pound mass. So we have M2. Now let's do M1. M1 is kind of the tricky one because we have a mixture. So M1 is equal to, it's going to be equal to the volume of the vapor over the specific volume of the vapor plus the volume of the liquid over the specific volume of the liquid. So this is going to be equal to 0.95 feet cubed over 0.29339 feet cubed per pound mass plus 0.1 foot cubed over 0.01413 foot cubed per pound mass. So then this works out to 10.3 pound mass. So we have M1 and M2. Now we just need M out, and from our mass balance we know that M out is just equal to M1 minus M2. So this is 10.3 pound mass minus 6.82 pound mass, which is equal to 3.48 pound mass. So now we have the mass that flowed out. So we have everything we need to solve this equation. Now we just need to plug everything in and solve it. So I'm going to rewrite the equation just because it's off the screen, but Q is equal to M2 U2 minus M1 U1 plus M out H out. And that's just a matter of plugging everything in. So we have Q is equal to, and so M2 was 6.82 pound mass multiplied by 108.51 BTU per pound mass. And then this is minus, and M1 is equal to 10.3 pound mass multiplied by, and actually I kind of skipped a step, so we need to calculate the internal energy of state 1, and so we want to kind of expand this and do a calculation with it because it's a saturated mixture. So U1 is equal to, and I'm going to put the mass in here as well. So I'm going to calculate all of this separate and then plug it into that equation that I'm solving. So this is M1 U1, and this is equal to the mass of the liquid multiplied by the internal energy of the liquid plus the mass of the vapor multiplied by the internal energy of the vapor. So then U1, this is a big U, is equal to 7.07 pound mass multiplied by 48.11 BTU per pound mass plus 3.23 pound mass multiplied by 108.51 BTU per pound mass, and this works out to 690.6 BTU. So then what I'm going to do is just plug this directly into this equation. So then if I do that, if I continue solving this, so I had the 6.82, which is M2, multiplied by U2 minus, and then I have U1, which is 690.6 BTU plus, and then I have M out, which is 3.48 pound mass multiplied by the enthalpy out, which is 117.2 BTU per pound mass. So then if I work through all of this, I get that Q is equal to 457 BTU. And we got a positive result, which we expect because there's heat input to the system. So let's just summarize what we did. Go back up here. So first of all, we set up the problem, and basically that just meant we did a drawing, figured out what we have, and figured out what we were solving for. We wrote our assumptions, and then based on our assumptions and what we're solving for, we wrote down the equations we need. So we needed a mass balance and also the energy balance. And remember, this energy balance that we used has a bunch of assumptions built into it, including that the change in kinetic energy is 0. So if that's not the case for your problem, you're going to want to go back to the more general form of the energy balance for non-steady state or non-steady flow, and start with that equation and cross out the terms that you know are 0, so then you end up with the correct form for your particular problem. Then we went ahead and looked up our data. So we needed to look up data for the outlet for state 1 and state 2. And then we solved our equations. And this right here, where I realized, oh, I can't just plug in M1 and U1 because that was a saturated mixture, so I need to calculate U1 from this saturated mixture. That's okay if you end up having to go back and do something and do a calculation or write another equation, because sometimes if you might get this far and then realize, oh, I actually need another equation, and so then you can just add that equation. So as far as writing this all out, if you think that you have everything written down, just move on with solving the problem, and you'll, as you're solving it, you'll realize things that you might have missed and be able to go back and do them.